Perfect. So let's go ahead.
Right. Okay. So as said a minute ago, I'm Scott Wesley. I'm going to be talking about verifying Solidity smart contracts in SmartACE. And this is joint work between my colleagues, Jorge, Navas, Valentin, um, Maria Christakis, Arie Gurfinkel, and Richard Trefler between Centura, Consensus, Diligence, the Max Planck Institute, and the University of Waterloo. So with that being said, I'll start with some motivation and background on this problem. So why we care about verifying smart contracts, what they are, and where the state of the art was before this work. So I'll start off with what a smart contract is. So at a high level, these are just finite state machines that manage assets on a blockchain. And often these contracts describe financial agreements. So as an example, an escrow service. So that's essentially just some third party that collects money on behalf of someone else and eventually releases that money if some conditions are met. So we can see on the right-hand side of this slide what this state machine might look like. It starts out in an active state in which users can deposit funds into the escrow. Eventually, the person who manages the escrow will either enable refunds if the conditions aren't met, at which people who deposited money can take their funds back, or the escrow will be closed when some conditions are met, and at this point, the beneficiary can claim their funds. I'll look at a few more examples of smart contracts on the next slide, but for now, let's just think about that example. So often smart contracts are written in the Solidity language. So this is just one programming language for smart contracts that's aimed at describing information flow between users. These users have addresses so they can be torn apart. And in the case of this escrow example, for instance, that information flow is describing the deposits made by those users and eventually whether or not that money is given to the beneficiary or not. And once this is turned into a Solidity smart contract, we end up with a program such as the one shown on the bottom right-hand side of the slide. So now we can see that these transitions such as close and enable refund now correspond to functions in this program. And the code of this function is what executes when these transitions happen in the state machine. So here are two more examples. The first one is an open bid auction. That probably doesn't require too much explanation, but we can see here that this starts off in a running state. Users can come along and place bids. These bids have to be increasing in size, and eventually some special user that we call it the manager will be able to stop the auction, at which point the largest bid wins and everyone else can withdraw their funds. In the second example, which is a bit more abstract, we have what's called an ownership interface. This can kind of be seen as like a library used right into smart contracts, and it describes that kind of ownership model used in the first two examples. So in the escrow, the owner would be the person or entity that decides whether or not the conditions are met, and in the auction, that would be the person who can stop the auction. So in this ownership model, we start out with some owner. They can transfer ownership to someone else, and this can go on until eventually someone might decide to announce their ownership, at which point no one owns the smart contract. So now that we have an idea what some smart contracts look like, let's take a look at why we care about verifying smart contracts. To illustrate this, I'll walk through a scenario of what the lifespan of that auction smart contract would look like. So in the beginning, a developer would come along and codify the rules of the auction in a Solidity smart contract. Once this contract has been written, it would be deployed to the Ethereum blockchain, which is kind of like a virtual machine that runs the smart contract. And once it's deployed to this blockchain, the code is immutable, which means that if, for example, a bug is found in the auction, no one will be able to fix it. Once this is deployed, users who want to take part in the auction, who may or may not trust each other, can come together and use this auction code to enforce the cooperation between each other, which would be the rules of the auction. The problem here is that we haven't really eliminated trust. We've just moved the trust into the source code rather than between the entities interacting with the code. So we'd still want to make sure that this code is correct, and we'd also have to make sure that it's correct under any sequence of transactions, which were those functions I described before. And because these entities can call these functions in any order, we'd want to look at sequences of transactions. So what exactly do I mean by a sequence of transactions? To understand this, let's take a closer look at the auction smart contract. So when we expand out what this contract actually looks like, we have a few state variables such as the manager, the leading bid, and whether or not the manager has stopped it yet. This is captured by the state of the smart contract. And we can see on the right-hand side of the slide that we have the state of each of these variables, and they're initially 0 initialized. We can see in particular that the manager's address is also set to 0. And this doesn't mean that a user with address 0 manages the auction, because in Solidity, the address 0 is actually more like a null address rather than a specific user. So this is actually saying no one owns the auction yet. In addition to the scalar variables, we also have a mapping that goes from the addresses of users to integers, and this captures the bid of each user. We can see on this slide that this array has 2 to the power 160 users, so that's a really massive number. And that's because on Solidity, the system is designed with 2 to the power 160 addresses used to index 2 to the power 160 users. So essentially, this is a massive state space. Once this is deployed to the Ethereum blockchain by some user, in this example, a user with address 10, which is referred to as the message sender, this constructor executes, and in this example, it just takes who the manager is. So on this slide over here on the right, we can see that that's set to 5. And this executes. And once this is done, the contract is constructed, and we now have a manager at address 5. So that's just a user whose address is 5. And then after this point, users can interact, alternating calling bid, withdraw, or if you're the manager, stopping the auction. So let's imagine some user with address 1 calls bid with a message value of 10. Because 10 is bigger than the initial bid of 0, we can see that the leading bid is now set to 10, and the bid of the user with address 1 is also set to 10. Now users will go back and forth calling these methods, and this would create traces of transactions, and these are the things we want to take into account during verification. So clearly, this is a pretty hard problem. Many possible traces and huge state spaces, so a lot of tools have been proposed for this problem, ranging from static analysis and fuzzing through to model checking and symbolic executions of single transactions, up to sequences of transactions. So these, and then on the farthest end, with not much automation, but with a wide range of properties, we also have deductive analyzers and computer-aided proofs. The limitation here is that most of these tools are specifically made for Solidity smart contracts. And since these kinds of programs are fairly new, these tools aren't the most mature. They have like they haven't had the decades of refinement, for example, in the areas of LLVM programs. Some of these tools do make use of existing verifiers, such as Seahorn for LLVM model checking, Boogie, and FSUP. But even in these cases, these tools are usually restricted to a particular kind of analysis. They don't. They do leverage existing tools, but they don't do it in a way that exposes Solidity smart contracts to the full spectrum of analyzers. So in our work, we've tried to develop a tool that can take a Solidity smart contract and analyze it using the spectrum of tools that already exist for fuzzing, symbolic execution, and model checking. And so this led to SmartACE, which is a tool that can verify intertransactional analysis, which is the kind of analysis I described on the previous slide. It can support multiple off-the-shelf analyzers. So in particular, we go from a Solidity smart contract to LLVM code, and then from there, we can take advantage of the range of existing analyzers that are well tested and quite efficient. We also do this translation in a way that's agnostic to the analysis decisions. So to give a concrete example, a lot of Solidity smart contracts involve multiplication because we're dealing with numbers, and you might be like, I guess a concrete example would be if you have an escrow, that might be collecting going from money to some other kind of currency. So you have to do a conversion by multiplication. And these kinds of operations are really easy for some tools to reason about, like fuzzes, whereas in a model checker, that might be a more challenging thing to reason about. So we don't want to make a decision early on. That would be hard. That would make certain analysis run well, but other analysis maybe not run well. So we try to defer these decisions to later on in the analysis. And finally, our tool is focused heavily around an idea of local reasoning, which was developed in some of our prior work. Essentially, the idea here is we have these smart contracts with a bunch of users and state associated to them, and that can be hard to reason about. So instead, we try to reduce this down to a smaller abstract model with just a few representative users. And in prior work, we showed that using these techniques in a early prototype of SmartACE, we could outperform an existing smart contract verifier called Verex by up to 10 orders of magnitude on their own benchmarks. So seeing this success, we wanted to see if we could push this into the whole spectrum of analysis. So with that in mind, let's take a look at how SmartACE actually works. So this slide gives a high-level overview of the entire architecture of SmartACE. On the left of the slide, we can see that we start by taking in a smart contract and some specifications. These specifications are given in the Scribble language, which is just one of many specification languages for smart contracts. Though Scribble is nice because it's a high-level language, so we can talk about contract invariance because we want to verify sequences of transactions. And through the tooling given by Scribble, we can reduce these specifications down to native Solidity instructions. So this means that even though we allow for high-level specifications, we don't really need these specifications to apply SmartACE. So long as there's some kind of assertions in the program, we can verify those as well. Once we go from a smart contract with specifications to a regular Solidity smart contract, this gets passed to the main tooling of SmartACE that goes from a Solidity smart contract to an LLVM verification problem. The first main component here is our source-to-source translator that does that translation. But as I mentioned before, we also want this translation to be agnostic to the verification decisions. So we've also introduced a novel runtime called libverify. This is an interface to the kinds of things that, about the points at which the model integrates with an analyzer. And by factoring this out, we can create different implementation of this library targeting each of the analyzers. In particular, SmartACE currently integrates the Seahorn model checker, libfuzzer for fuzzing smart contracts, and CLE for symbolic execution. In terms of verification, we use the technique from our prior work called PCMC to do local reasoning on smart contracts, and we also support fuzzing, symbolic execution, and bounded model checking for bug finding in smart contracts. So now that we have an idea of how SmartACE works end-to-end, let's take a closer look at how the source-to-source translation actually is applied. So on this slide, we can see the entire pipeline of the source-to-source translation, starting from a smart contract and ending with the LLVM verification problem that we call the harness. In particular, I'm going to look at 3 stages in this pipeline that separate SmartACE from existing tools. A lot of these other stages are fairly similar to other tools and can be read about in the floor paper. But with that said, the first unique stage in this pipeline is what's called participation analysis. This allows us to take a smart contract and to identify those representative users that can be used for smart contract PCMC. So for example, in the opt-in smart contract from before, we can see that this manager address always keeps track of one special user that might show up in these different transactions. So that implies that if we wanted to find a few representative users, one of these users would be the manager, and that manager is always one specific user. There's other kinds of participation that can go on, but this has all been covered in prior work and can be read about in more detail in the full paper. In terms of how we go from a smart contract to these few representative users, we make use of an algorithm called PTG Builder that was also introduced through prior work. And as mentioned early on, was demonstrated to allow SmartACE to outperform, identify sufficiently precise to reduce the uses significantly enough that we could actually outperform existing tools. So once we've identified these 3 representative users, we still have the challenge that these maps are massive. So the next step that's quite important is how we actually represent maps and reduce them down to smaller representations. So in Solidity, the map lookup is actually quite complicated. We have these giant maps. We don't map directly from addresses to mapping. There's actually some hashing going on and a lot of other complicated details. But in terms of most analysis, these details are actually taken for granted. And since we're focusing on higher level properties, they don't matter too much. So, we actually allow for maps to be parameterized either by participation analysis if we're doing verification, or by a user provided parameter if we're doing bug finding. And then we map directly from addresses to mappings to simplify the analysis. Once all of these transformations have been done, we output the LOVM-based harness that we actually verify. At a high level, it's essentially just an execution loop that models a sequence of transactions being executed against the smart contract. So let's take a closer look at how this model actually works. In the beginning, we set up the blockchain and the smart contract construction. The details on how we deal with addresses and the blockchain can be found in the 4 paper. In terms of contract construction, the models we generate essentially follow the same rules explained at the start of this presentation. And then once the contract is constructed, we enter this execution loop. At the start of the loop, we check to make sure that the property is satisfied after construction. And once we go through this loop again, we continue to check that the property is still satisfied after each transaction. And if the property is violated, we raise an error in the analysis. Otherwise, we go on to generate a transaction and to execute that transaction. Once again, the way we represent these transactions are essentially how was described earlier in this presentation. And then after each of these executions, we also have to, so after each of these executions, if we're just doing bug finding, that's fine, and this step is skipped. But if we're doing parameterized verification, we have to do a bit of extra work because we've reduced down to a few users and we want to be able to generalize to any number of users. We do this through a technique called interference abstraction. So this can be found in more detail in our prior paper published in SAS 2021. But the main point here is that this interference can actually be found automatically using a new synthesis procedure that we introduced within the C1 model checker. This allows us to automatically find the interference. We also allow for the interference to be provided manually, and that can be a bit faster, but as will be shown in the evaluation, in the cases we've looked at, finding the interference automatically is quite comparable to providing it by hand. So now that we have an idea how SmartACE works, let's take a look at some of the limitations. So first of all, we have some standard limitations, assumptions that show up in most tools, such as the fact that we don't deal with Solidity assembly because we're dealing with high-level properties rather than low-level details of single transactions. We don't model reentrancy. For those who are familiar with smart contract analysis, you're probably aware that best practices in smart contract development already avoid reentrancy, and tools exist to ensure that these best practices are already met. So we decided that that wasn't worth, tools already exist that can deal with this, that can be applied to a smart contract even before SmartACE is used. So we work under the assumption that those best practices are already met. We also assume that the number of smart contracts that we're analyzing is bounded, and this assumption in some form or another shows up in most analyses. We also have a few limitations that were introduced from the prior work on parameterized analysis, specifically that mappings go from addresses to numbers, and that these addresses are only compared for equality and disequality. In our experience, these assumptions are sufficient for smart contract, the analysis that we have done. And since SmartACE is a prototype, there's also some features that just haven't been dealt with yet, such as gas, low-level features like cryptography, calls to external contracts with unknown specifications, and also some of the finer details of time. In terms of time, we can deal with properties so long as they don't deal with events happening in the future, so like liveness, like saying eventually something will happen. And these are pieces of future work to extend SmartACE. So now that we understand what SmartACE is and what it can do, let's take a look at our evaluation. So the goal of this evaluation was to determine if SmartACE and Scribble were efficient for real-world smart contract verification, to identify limitations of the challenges and limitations, and to determine if parameterization had the effect on verification that we expected. So for this analysis, we looked at two smart contracts from a popular library called OpenZeppelin, specifically the ownable interface and the refund escrow, and ACE. And we also looked at an auction due to some novel properties that I'll discuss in a moment. So in terms of specifications, Scribble allowed us to describe pre and post conditions on functions, and also contract invariants. We could also specify temporal properties, such as if some function is called at least once, then some property holds. This wasn't supported directly from Scribble, but could be done easily using standard techniques as described in the paper. And using these techniques, we were able to describe most of the properties of interest, such as if close has been called at least once on the escrow, then refund has not been called. However, there were a few properties that required a bit more work that I'll talk about briefly. The first kind of property, which we call universally mapped quantified properties, are properties that talk about all entries in a map. So for example, in auction, we wanted to verify that if we choose any two users with non-zero bids, then those bids are unequal. This is challenging if we did it directly, because we'd have to quantify over every element in the map. And because these maps are big, that's not very efficient. However, this is equivalent to just choosing two users up front arbitrarily and making sure that those two arbitrary users never have the same bid. And using this, as will be shown in the numbers soon, this proved to be efficient. And as shown in the paper, it's quite easy to also instrument on this level of Solidity source code. The second kind of property we looked at were aggregate properties. So these are quite common in smart contract analysis in the form of sum aggregates. So for example, in the case of our escrow, if the escrow hasn't been closed and the funds haven't been released to a beneficiary, then the sum of all of the deposits should be the balance of the escrow. To reason about aggregates, we need custom proof rules. So in the case of sum, for example, if we add a ghost variable that keeps track of all the sum of every element written to a map, then we can use that ghost variable in place of the sum and verify properties. This kind of technique is common in prior work. However, we were also faced with some new aggregates that didn't appear in prior work. So in the case of the auction, for example, we wanted to prove that the maximum bid was equal to the leading bid. And this required a new proof rule, so I'll outline that briefly on the level of the source code. So to verify this property, we started by introducing two ghost variables. The first ghost variable tracks the largest value written to the map, whereas the second ghost variable ensures that the elements are increasing. We then, after each update to the map, would update the maximum element and check if the new update was increasing from the previous value. If we can show that the updates are always increasing, then we can use the maximum value written so far in place of the max in any property. And in the case of the property we want to verify, this technique was sufficient. So now that we have an idea of the properties and the challenges faced instrumenting them, let's take a look at the actual verification results. So I'll run through this quickly just due to time. First, we found that our properties could be verified using PCMC, local reasoning. We also found that after fault injection, we were able to find bugs for all of the properties using all three techniques described early on. when we increased the number of users from 5 to 500, we found that these techniques were no longer feasible. So this justifies a hypothesis that parameterization is essential for smart contract verification. We also found that all but one property could be verified using default interference, which I don't have too much time to go into that, but essentially that's kind of like assuming any user can have any value. So basically the weakest assumption we can make on users. And in the case of the one property that did require interference, we found that synthesis was able to find an adequate invariant, and it only increased analysis time by a few minutes. So it seems to be feasible, at least in that case. So now all this has been said, that brings us to the end of this presentation. So in conclusion, SmartACE is a smart contract analysis framework that focuses on parameterized verification. It enables existing analyzers for LLVM code to verify smart contracts and take advantage of the power of these tools. And as shown early on, SmartACE makes use of PTG builder and participation analysis to make local reasoning possible. And as shown in our case studies, SmartACE can be used to verify real-world smart contracts. So all of these experiments and the tool itself can be found on our GitHub page. So with all that being said, I'll turn it over to questions.
Okay, thank you for your presentation. Thank you so much. So again, I will start from in presence questions. If
let's see any questions here. I actually have a quick question. Can you just say a little bit more about the interference synthesis algorithm?
Sorry, what was that question?
Tell us a little bit more about the interference algorithm.
Oh, sure. So I guess at a high level, what's going on is originally in Seahorn, what we were doing was trying to find a single predicate that could describe the state of the smart contract after each transaction. However, when we have the interference, it's kind of like we want to find two properties now. One that summarizes each element in the map, and then one that summarizes the overall state of the smart contract. So now we're trying to find two invariants rather than one. So the underlying tools used in Seahorn are able to solve nonlinear problems like that. But the model, like the actual, so I guess to take a step back, the Seahorn tool is used to model check C programs, whereas, well, LLVM programs in general, whereas the underlying tool spacer is just a solver for logical problems expressed in constraint Horn clauses. So the problem we faced there was trying to express on the level of LLVM programs the fact that we wanted to find these two invariants. So that work is still ongoing and will hopefully appear in some of our future work. But the high level is we're trying to find two invariants now. Does that answer the question?
Yes, thank you.
Okay, we have a question from Hermit, so from Long Fam. Thanks for your nice talk. Can you give me an interesting realistic correctness properties of a smart contract that is not expressible in Scribble?
So I guess one example that we did actually try to verify, and so the two examples of properties I looked at in detail were actually properties we couldn't express in Scribble, but that we could still encode if we changed the smart contract. So I guess two interesting properties then would be reasoning about the maximum element in a mapping and reasoning about things quantified over all of the elements in the mapping. So in the paper, we actually proposed that extending Scribble to deal with these kinds of things could be nice for future work. Beyond that, we haven't those are the only properties we ran into so far in our work, but Scribble is still like a very new tool that's being developed, so I'm sure you could find a lot of properties that might require some extensions to the tool to make it possible.
Okay, so okay, perfect. So let's thank again the